What if a single device could turn compressed air into both hot air and cold air at the same time? That is exactly what the Vortex tube, more specifically the Rankine-Hilsch Vortex tube, is able to do. A Vortex tube is a simple mechanical device that uses compressed gas, usually air, to separate a single inlet flow into two outlet streams, one hot and one cold. Compressed air enters through an inlet near one end of the tube. Because the air enters tangentially, it begins spinning at extremely high angular velocity, creating a strong vortex inside the tube. That spinning motion is what sets up the rest of the physics. Once the air is rotating, the pressure inside the tube is no longer the same everywhere. A radial pressure gradient forms. That means the pressure is higher near the outer wall and lower near the center. In simpler terms, the outer part of the flow gets pushed outward and compressed more strongly, while the center remains at lower pressure. As the vortex develops, two main flow regions appear. Near the outside of the tube, there is an outer vortex that moves toward the hot end. Near the center, there is an inner reverse vortex that turns around and flows back toward the cold end. And the hot end valve is a major part of why this happens. The valve restricts how much air can immediately escape from the hot side. Because of that restriction, not all of the air can simply continue straight out. Some of it is forced to turn around and move back through the center of the tube. Now that we have the physical picture, we can start analyzing it more carefully. A good place to begin is with how the incoming air is split between the hot outlet and the cold outlet. To describe that, we use mass fractions. The cold mass fraction is written here. This simply means the cold outlet mass flow rate divided by the inlet mass flow rate. It tells us what fraction of the incoming air leaves through the cold side. The hot mass fraction is also written, and that tells us what fraction of the inlet air leaves through the hot side. Since all of the air entering the tube has to leave through one side or the other, conservation of mass gives us a mass fraction of 1. This result tells us the two mass fractions, both hot and cold, must account for the entire inlet flow. So now the next question is the big one. What actually causes the temperature separation? Why does one part get hot while another part gets cold? The short answer is that energy is being redistributed inside the tube. The higher pressure rotating outer flow gains energy. The lower pressure inner returning flow loses energy, and because of this, the outer flow becomes hotter and the inner core becomes colder. Now let's connect that to the first law of thermodynamics. For a steady flow control volume, the general energy equation is written. This equation says that the energy entering a system plus any heat added minus any work done must equal the energy leaving the system. For a vortex tube, we usually make several standard assumptions. We assume steady operation. We assume negligible heat transfer with the surroundings. And we assume no shaft work. With those assumptions, the energy equation is simplified. This is one of the most important equations in the analysis. It tells us that the energy coming in with the inlet air is equal to the energy leaving with the hot and cold outlet streams. So again, the vortex tube is not creating energy. It is redistributing it. One thing that makes the vortex tube unusual is that velocity cannot be ignored. In many thermodynamics devices, we simplify by neglecting kinetic energy changes. But here, the gas is spinning intensely, so velocity matters. The total velocity can be written. Here, Vr is the radial velocity, v theta is the tangential or swirl velocity, and Vz is the axial velocity. That tangential velocity can be very large, and that means rotational kinetic energy can be a major part of the energy balance. To make that clearer, let's rewrite the energy balance using mass fractions. Using the solved energy equation from earlier, and if we divide through by the inlet mass flow rate, we get the following. For ideal gas air, enthalpy is specific heat capacity times temperature. So the equation is simplified, and if we divide by specific heat capacity, we get this. From this equation, we can write the stagnation temperature as well as the energy balance. This is a powerful result, because it tells us that the vortex tube is not just separating static temperature, it is redistributing total energy. And total energy includes more than just internal energy. It also includes kinetic energy. That part matters. For example, suppose the air inside the tube is swirling at about 200 meters per second. For air, the specific heat is about 1005 joules per kilogram Kelvin. If we express that kinetic energy in temperature units, we get that the motion of the air alone can account for a temperature equivalent contribution of about 20 Kelvin. It helps explain why the energy balance in a vortex tube has to include both thermal effects and flow motion, not just temperature by itself. Now let's look at one of the key engineering trade-offs. We can start from the temperature balance. Since the hot mass fraction can be written as 1 minus cold mass fraction, we can substitute it into the balance equation. Expanding and rearranging this equation, we obtain the following cold side temperature difference, which shows how strongly the result depends on the cold mass fraction. If you want colder air, you have to produce less of it. That is one of the central trade-offs of the vortex tube. A smaller cold fraction can produce a colder cold stream. A larger cold fraction gives you more cold air, but usually not as much cooling. And that is exactly why the hot end valve matters so much. By changing the valve restriction, you change the flow split. And when you change the flow split, you change both how much cold air comes out and how cold it becomes. Now let's talk about performance. A common way to evaluate a cooling device is with the coefficient of performance, or COP. For refrigeration, COP is defined, where QL is the useful cooling rate and W dot in the required work input. Now, the vortex tube itself has no moving parts and no shaft work, but the compressed air entering the tube had to be produced by a compressor. So, if we are evaluating the real system, the true work input is the compressor work upstream. If we treat the cold outlet as the useful cooling effect, then the cooling rate can be approximated here. So an approximate COP becomes the following. This tells us how much useful cooling we get compared with the energy needed to compress the air in the first place. And in general, the vortex tube does not have a high COP compared with conventional refrigeration or air conditioning systems, so it is usually not chosen because it is the most efficient option, but because it's simple, compact, and reliable. Finally, let's compare the vortex tube with an ideal benchmark, such as an isentropic expansion. An isentropic process is both adiabatic and reversible. For air, the outlet temperature of an ideal isentropic expansion is the following. This equation tells us how cold the air could become in an ideal expansion across the same pressure ratio. Now, the vortex tube is not the same as an ideal nozzle or turbine. Its flow is much more complicated. It includes turbulence, internal energy redistribution, 2 outlet streams, and irreversible mixing. But it is still a useful benchmark. If we call the ideal outlet temperature Ts and the actual cold outlet temperature Tc, then we can define an isentropic cooling efficiency as the following. The numerator is the actual cooling achieved by the vortex tube. The denominator is the ideal cooling predicted by reversible isentropic expansion. This ratio tells us how much of the ideal cooling potential the real device is capturing. If that number is close to 1, the device is performing near the ideal limit. If it is much lower, then irreversibilities such as turbulence, viscous dissipation, shear, and mixing are consuming much of the available pressure energy. This simple device reveals just how powerful the principles of thermodynamics and fluid mechanics truly are, especially in a device with no moving parts that can produce both hot and cold air at the same time.